Okay, so I already forgot what we saw in the last class. Was a long time ago. Anybody remembers? Well, anyway, today we'll see uh, three related topics: fractal information and semiotics. Let me forget about this screen because it's just blinking, switching on and off. Right. So, I mean, have you heard about fractals? Have you heard the word fractals? Yeah, if you watch Frozen, then in the song Let It Go, they mention fractals, but which suggests that it made it reached mainstream vocabulary. In the 80s, they became very popular because there are nice visual patterns and kind of psychedelic looking, especially if you choose the wrong colors. Um, and I mean, we'll go through the story of fractals, but one of their characteristics is that they are self-similar objects, meaning that they are similar at multiple scales. It's not, I mean, in many cases, when you zoom in a fractal like this one, then you will find again the same pattern that you started with. Um, in some cases, not exactly the same, but it's similar. So that's enough to qualify it as fractal. And actually, uh, they became very popular, um, and then they kind of drifted away from the attention of most scientists. So it's uncertain why there aren't many new papers exploring fractals. Maybe everything that should be known about fractals is known already. Maybe um, maybe there are something just waiting to be discovered. Of course, we can enter the discussion on whether mathematics are discovered or um, uh, created, let's say, or constructed. But more recently, it seems that a challenge is to study self-dissimilarity. I mean, systems that are not similar at multiple scales. Like, for example, uh, let's say our societies are different from individuals, or cells are different from multicellular organisms. And let's say the study of self-similarity can be useful to study also and understand self-dissimilarity. And uh, we can say that fractals study roughness. So in geometry from ancient times, in Egypt, China, India, Greece, people work with smooth geometrical objects like straight lines, squares, triangles, circles, ellipses, parabola, and so on. And all of those are smooth, and it's great. But then we look at nature, and it's like very difficult to find smooth surfaces. So we see mountains, we see trees, we see snowflakes. I don't know whether you've seen the big ones that because you probably have seen these pictures of snowflakes that have this six-fold symmetry. Um, but when the atmospheric conditions are right, I mean, they can fall and you can see those not only in the microscope, but let's say just with your eye, they can go really big. Maybe next winter. Um, and when one has self-similarity, that naturally gives you a distribution that it's not normal because you end up with few big ones and many small ones. So it's not a coincidence that many fractals have scale-free distributions in many properties or scale-free like distributions. And they can be used to produce realistic looking waves like in this wood print from the, is it 18th or 19th century, this Hiroshige? I forget, but let's say long time ago in waves, mountains, rivers, capillaries, trees, broccoli, and so on. And so yeah, all fractals have scale-free properties, but not the other way around, in the sense that many scale-free systems are not fractals. Uh, Therefore, it's also related to 1 over F noise, which Mandelbrot, who is considered the father of fractals, also studied, which is basically, let's say, most fractals we are used to are spatial, but then you can study very similar phenomena in time, and that's 1 over F noise. So probably you've heard of this very popular book, Gödel, Schrambach, and Eternal Golden Braid. So there's a study of how there's recursion in some of Bach's pieces, which could be said that it's like an acoustic fractal. Uh, Also, there's a link with chaos. So all chaotic attractors are fractals. Why? We don't know, but that's the case. Um, and we can start with Cantor, who was working in Germany in the late 19th century. He was accused. Well, he developed set theory. Well, I'll go a bit back. So, um, since ancient times, people didn't know how to deal with infinitesimals nor with infinite numbers. So, for example, irrational numbers did not exist until Cantor defined them properly. Um, so, for example, one could speak about square root of 2, but it was like a taboo, even when from uh, Pythagoras theorem, we know that if we have a square triangle, the length of each side is 1, then the hypotenuse would be square root of 2. But let's say in Greece, especially in the Pythagorean school, there was this idea about the perfection of numbers, and irrationals were not perfect, so they kind of shone them under the carpet for a couple of millennia. And since the Greeks were using ratios rather than numbers for geometry, this wasn't a big problem for them. But let's say later it kind of was problematic that you couldn't speak about square root of 2, square root of 3. Uh, Pi was kind of ambiguous because you can calculate some digits and then let's say, well, there's still many mysteries about pi, but anyway. So anyway, Cantor defines set theory, which is the basis of modern mathematics, but he found many paradoxes there. So he was called charlatan, corrupter of youth and wars uh, by many illustrious um, mathematicians and scientists like Henri Poincaré, his own advisor, that was he Kronecker? No, I'm confusing. No, Kronecker was kind of his contemporary and was discovering similar things. Yeah, I forget the name of his advisor. He was also kind of speaking bad about him and putting him obstacles like he applied for a position, and then his advisor kind of interfered so that he wouldn't get that position. And oh, anyway, yeah, because he found paradoxes dealing with infinite sets. And then Bertrand Russell tried to fix those. He couldn't. Hilbert tried to fix those. He couldn't. Gödel proved that you couldn't prove them. And let's say all of this has basis in Cantor's work. No, it was Kronecker. Well, anyway, Wittgenstein also spoke about Cantor, that what he was doing was utter nonsense and it's just laughable and plainly wrong. Uh, we will see later about Charles Sanders Peirce and semiotics, and he understood his work. Actually, Hilbert praised Cantor highly. And anyway, entering into fractals, this is known as the Cantor set, which actually was discovered by Henry John Stephen Smith. So this an example of the so-called Stigler's law of eponymy. This Stigler's law states that no scientific discovery carries the name of its original discovery. And of course, this was already discovered by others before Stigler, so it verifies itself. And it's self-similar. So it's very easy to construct. You take the segment 0, 1, and then you divide it by 3 and remove the segment between 1/3 and 2/3. So you end up at the second iteration with 2 segments from 0 to 1/3 and from 2/3 to 1. And then you repeat for each piece the same procedure. You divide in 3 and remove the central third. So we end up with 4 segments from 1 to 1/9, from 2/9 to 1/3, and so on. And then you keep on repeating. And you end up with, let's say, smaller and smaller segments, but you end up with more and more segments. So of course, this set is infinite. And it's also self-similar, because if we look, let's say, just the left branch, then it's the same as the other. And since it's infinite, you can show that the cardinality of a subset of the Cantor set is equal to the cardinality of the whole set. And that seems like a paradox, but that's how infinites work. And that's why actually there are some people who don't believe in infinite. Just to get rid of these paradoxes. And yeah, when one deals with infinites, one gets into funny situations. So a few years later, around the turn of the 20th century, well, 1904, Helge von Koch proposed the Koch snowflake. And here in that logo, there's a little model that, well, here. So do you see what happens? Oh. Yeah, so basically in the snowflakes, we do what I will explain 3 times. So similar to the Cantor set, you take one line and then you divide it in 3. But then instead of removing the central part, you add 2 segments of the same length. So we end up with kind of a spike. So now we have 4 segments. In the Cantor set, we start with 1 segment and we end up with 2. Here we start with 1, we end up with 4 of 1/3 the size. And then in the next iteration, we do the same for each of the 4 segments. So remember here there was a segment, and then we divided by 3, and the central one we remove and add this spike like an equilateral triangle. And then we repeat that, and repeat it, and repeat it, and repeat it, and repeat it. Oop. Well, let me do less so that we can see more or less. You cannot really see it. Well, anyway. So what we end up is with a smooth curve, because, sorry, the opposite. It's not smooth curve at all. Definition of a smooth curve is one that has a defined derivative in all of its points. So for example, if you have a line and then like a sharp turn, in the turn, like in the spike, their derivative is not defined because let's say it can, yeah. So until this moment, it was assumed that um, continuous curves would be derivable in all their points, and this is one example of a curve that's it's not derivable in all of its points, because when you iterate this towards infinity, in the limit, every point in the curve is non-derivable, but still, let's say it's continuous, it looks smooth, but it's actually very rough. Yeah, so here one can see how it is, and if you do this 3 times as the size of a triangle, let's say you end up with a so-called snowflake. And it's something I did like in a chessboard, and then you start doing iterations. So towards the center, you end up with these Coq curves as the sides of each of the squares. And in 1915, let's say 10 years later, Václav Sierpinski proposed his triangle, which is also similar in the sense that you start with a triangle, divide by 4, remove the central triangle, and then you end up with 3 triangles. Then you end up with 9 triangles, do the same, 27 triangles, 81 triangles, and so on. And was there in NetLogo something like this? So I forgot how this one does it. Remember that with elementary cellular automata, there also, I think it was rule 90, produces a very similar pattern. Yeah, so there are many ways of constructing this. You can also do with a square, you can do it in 3 dimensions. Let's say it's similar mechanism. So for example, here I did the same, but let's say with curved lines instead of triangles, and then you get this pattern, and then you arrange them in a triangular grid, and then they look hexagonal. Yeah, so actually, Sierpinski was in contact with, yeah, if I remember properly, in those years, Lviv, now in Ukraine, in Western Ukraine, was part of Poland, and there was like a mathematical school that was interested in this type of problems. And the uncle of Benoit Mandelbrot, that we will mention in a moment, Zolem, he was living there and was interacting with Sierpinski, and Sierpinski advised him to leave Poland and and later he went to Paris. And let's say that in a way also sealed the fate of Mandelbrot and his family, because they also left Poland to Paris. And in, in those years, well, a bit later, it's in the early 1920s, more mathematicians, well, French mathematicians were studying iterative functions, which is very similar to these processes, but let's say just mathematically on the complex plane. So these are Julia sets, and its complement is called the Fatou cloud. Sorry, Fatou dosts, or yeah, also Fatou sets. So they're constructed by iterating complex functions. So the complex plane, you have real numbers and imaginary numbers, and then you iterate functions like a number to its square power, and then you see how long it takes to go out of a certain radius. Depending how many iterations it takes to go out of the radius, you draw it in a different color. And then this gives us this pattern, this type of patterns. And well, this is sum on the Mandelbrot set. It's Beno Mandelbrot. Actually, it was defined by Brooks and Metelsky a few years earlier. So again, this law of eponymity. And it's a generalization of the Julia sets, just as a constant, so then you can get richer patterns. And let's say you can see how mesmerizing it can be. Again, it has many interesting mathematical properties. It can be seen as a map of well-connected Julia sets. Yeah, has many interesting mathematical properties. It also has you can find Feigenbaum's constants, which were discovered in bifurcation diagrams of chaotic systems, so-called doubling root to chaos. So there's this Feigenbaum constants like 4.66 or something like that, an irrational number, and you can find those in the Mandelbrot set. Don't really know why, but yeah. I mean, the story of Mandelbrot is interesting in itself. So his uncle Solem advised him to do his PhD in studying these recursive functions, sorry, iterative functions, but it was like too complicated, like he couldn't. And then he did his PhD on something else. And then he actually did one postdoc with Norbert Wiener and another postdoc with John von Neumann, which is like, what? And later he ended up in IBM. And in the 70s, before personal computers, not many people had access to processing power, and he did. So, I mean, I don't have data, but I don't have doubts that big reason for why he could start exploring this is because he had access to computers with not only computers, but with good graphics. And what else from Mandelbrot's story? He was interacting also with Piaget and with what's the name of this sociologist who made this Stanley Milgram, yeah, who did these experiments of the 6 degrees, and also experiments on questionable experiments on human torture. Well, anyway, Astrid Lindenmayer proposed so-called L systems or Linder-Meyer systems, and they can generalize many fractals already mentioned, and also others. And also they use the so-called turtle graphics that were defined also with Logo in the 60s, the grandfather of NetLogo. So for example, you start with a root and then you have different rules and then you end up with this type of patterns. And then you can vary the parameters. Then you end up with different patterns and so on. So you can play with this. Yep. Wait, why does it look just the same? Yeah. So basically, L systems use this idea that you have one segment and then you have an iterative function that replaces that segment with, let's say, a sequence of segments with additions or rotations, translations, removals, and things like that, like the Sierpinski triangle. And then you end up with more segments, and then you repeat that process. And in some cases, you can also add some variations to it. Yeah, so like for example, here you start with one line and then you divide it, and then you don't. Yeah, I mean, of course, you can do the same and then you'll get the same pattern here. But let's say you repeat that gemation process. So from these lines, you sprout more lines. And from these 4 lines, you sprout 8 lines and like that, and you end up with that pattern. Yeah. Okay. Any question about fractals?
Mentioned that chaos follows fractals.
Mhm.
To me, fractals look like a very pleasant, symmetric pattern, but chaos is supposed to be like erratic or asymmetric patterns.
Yes.
Where is the connection coming in what sense?
Yes. So actually, in many cases, in chaotic systems, you never reach the attractor because the so-called transients, which are all the states that lead to the attractor, are where, let's say, almost infinite. But then in many dynamical systems that have been well studied, then you have the, let's say, just the attractor, and then you can see that these are fractals. Well, so for example, these ones, yeah, so there are different chaotic attractors and they're fractals. So the classic Lorentz attractor, this one, yeah. Okay. Yep.
So, is the concept of golden ratios related to fractals, the idea that keeps everything?
So the golden ratio can be constructed recursively. So for example, the golden spiral, since, for example, you can construct it like with two squares. So you have like length 1 and 1, and then you put another square of size 2 next to it, and then you have like 1, 1, 2, and then you put another square which would be 3, and then you have 1, 1, 2, 3, and then you put another square which would be 5, and then you put another which would be 8, and like that. Yes, yes. So that is recursive. Well, can be recursive, but can also be iterative. And let's say it gives you a self-similar pattern, you know, because since the Fibonacci numbers are the sum of the previous two numbers, let's say it gives you the same proportions. And then the golden ratio, it's the Fibonacci n plus 1 over Fibonacci n when n tends to infinity. But there are other ways of calculating the golden ratio that don't involve fractals. So, yeah. Okay. So, I mean, information, I think it was always relevant, only that it was after computers that we had the tools to study it. So we can identify three revolutions in our civilization: the agricultural, which was mainly about controlling matter; the industrial, which was mainly about controlling energy; and information revolution, that I guess we are still in the process of living it, which is about control of information, obviously. And let's say having computers to process information, well, not only computers, but also information and communications technology to store, transmit, and process information at rates that we were unable to do, has allowed us to study intelligence, which, independently of the definition we prefer, it's about information processing. Also allows us to study complexity, because we need lots of information to model interactions. And also cybernetics, because control at the end, it's about organization, and we'll see that organization is can be very similar to information. So there's this book by James Gleick, Information History, Theory of Law. Highly recommended. And the book starts speaking about talking drums in the Gambia River in West Africa. And these were used until a few centuries ago for communication between villages. So, I mean, people still use talking drums, but they don't use them for communication. They have WhatsApp, but anyway, you have basically two nodes in these drums, like high and low. And then, interestingly, they codified the information not like something like a Morse code, but it was just natural language. But then in natural language, we have many more phonemes. So if we just translate letters into tones, ta 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 ta. Ta 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 ta. So it becomes very ambiguous, because there are many different words or phrases that would fit the same pattern of up and down, no? Or with two sounds. So what they did was to add redundancy to phrases. So instead of saying the moon, which would be tata, there are many other things that could be like that. They would say like, oh, the beautiful one shining in the sky at night, ta 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 ta. And then that would be understood like, oh, they're speaking about the moon. So by adding redundancy, they could use just two symbols. And I mean, I say symbols because they're sounds, but of course they can be used for transmitting information. And it's very interesting that before the first telegraph cables were laid down, uh, the transatlantic cables, the fastest that you could send information, let's say, from New York City to London would be maybe one week, the fastest steamboats, if no icebergs were on the way. And suddenly you could transmit information at the speed of light, uh, with electricity. And of course, Morse code, it's one of many codes, but then it became more relevant to study different codes. And also, yeah, I mean, if you took the 500 course, then you know about coding and its relevance. And it's also relevant with cryptography. So, for example, in the Munich Museum of Science, they have a huge exhibition of cryptography since ancient times. And let's say there are many interesting relationships between trying to cipher messages, um, and information and communication and computer technology. So we might be more familiar with the Enigma machines that Alan Turing was working with during the Second World War. And but also there were, since ancient times, many different ways in which messages were ciphered. So one easy way is to have a text that, let's say you have your alphabet and then you replace the symbols for other symbols. In some cases, those symbols might be invented and then you are like looking at gibberish. In others, you just shift. So let's say instead of A, you choose C, instead of B, you choose H, and so on. However, those are easily decrypted because, for example, in English language, the most frequent letter is E. So if you get a encrypted message, you can just say, okay, which is the most frequent symbol, and then you assume that one is E. I forgot what's the second most frequent, and then you assume that's one of the frequent symbols, and after you get those frequent symbols, then you start deciphering others, like playing hangman, when you have some letters, and then you guess the rest. So yeah, during the Second World War, in the initial stages when they were using the Enigma machines, one thing that facilitated the decoding is that the submarines ended all their messages with Heil Hitler. So they could use those, like, okay, at least we know which codes are those letters, and then they could start decoding the other letters. And of course, the trick of the Enigma machines was that they were changing the code almost every day. But it's interesting that in the newspapers in London in the 1840s, so almost 200 years ago, there were articles that spoke about the nervous system for the planet using telegraphs. And let's say that, of course, with the internet, became more realistic. And then around the turn of the 21st century, people spoke of a global brain, and let's say some of that research is more serious than other. But anyway, we can see information as entropy. So Claude Shannon, I mean, we already mentioned him in the first class about history. and I mean in cybernetics, and he was also working in the Second World War with ciphering messages, and he came up with well, in his paper, Mathematical Theory of Communication, that was one we already read and discussed. He proposed this measure of information. Later, he kind of regretted to use that term because it was confusion, and then let's say it became like a fad, and everybody was saying that now that we understand information, we'll be able to do everything. So he has a later article where he kind of brings down and kind of criticizes all those enthusiasts that, let's say, were making groundless claims. But von Neumann suggested him to call it entropy because nobody really knows what it is. And actually, the equation of Shannon's information is the same as Boltzmann-Gibbs entropy. And we can say that organization is the inverse of information. Of course, it depends on which information, because Shannon information was interested about the amount of information we get when we receive symbols. So how much information the symbol carries. And Wiener proposed a measure of information which was the same as Shannon, but without the minus sign. So Wiener understood information as the information you already have. So if you have lots of information, then you can predict all the symbols that you will get. So then that's high information of a probability distribution. And then Shannon is the opposite. If you can predict all the let's say which symbols you will get later based on a probability distribution, then the new bits you receive don't carry any information. But anyway, we can say that organization is the opposite of Shannon information or equal to Wiener's information. And interestingly, this is beyond physics. Stuart Kaufman, in his book Investigations, has the so-called biosphere blended thought experiment. So imagine you grab a biosphere like ours, put it in a giant blender and press maximum. So after some time, you will still have the molecular richness that we have, because let's say the blender doesn't break molecular bonds, but it breaks the organization that creates and sustains those molecules. So the molecular richness will very quickly degrade. And an important thing about Shannon information is that it's syntactic, so it doesn't care about meaning. And we can say that computation is transformation of information. And of course, there are many limitations. And since then, we've seen many exponential increases in transmission, processing, and storage of information. So the most famous of this is Moore's law, that says that every 18 months, the number of transistors per square centimeter has been doubling. But yeah. So let me put this here. So number of transistors for microchips doubling every 2 years. This is a microchip. I thought the original one was on per square centimeter, that it had already started leveling. But anyway. So let's say in 1970, 1,000 transistors per microchip were in 50 billion. Of course, if we make larger microchips, they can keep on increasing, but Yeah, there are limits to how small they can be. But anyway, one can get similar exponential increases. So this is in semi-log scale. And so, for example, the cost of stored megabyte has also gone down exponentially, or in some cases even faster. So this led some people to claim that singularity is approaching, but in order to have a singularity, we would need hyperbolic increase, which we don't have. And anyway, probably this will at some point level off. So then we will have more like a sigmoid curve, like an exponential curve that just keeps on increasing until infinite. But anyway, in an exponential curve, it reaches infinite only when the time is also infinite, even when it doubles every 18 months. So yeah, in order to have a singularity, we will need hyperbolic growth, which we don't have. And even if exponential laws continue, we've had software crisis, so-called already since the 1980s, because the improvement of software hasn't been exponential and in some cases not even linear. So for example, the scores of uh, chess playing machines programs has been more or less linear, more or less in the same period, because chess is a combinatorial problem, so you need an exponential increase in capacity in order to have linear increase in performance. And I would say that one of the challenges for AI is that of meaning. So that is given precisely by semiotics, which is the part of information that we assume. And in many cases, we will see that LLMs also don't have any semantics. They don't understand meaning. They just process information, and that can be useful in many ways, but it's also a limitation. So whether we'll have utopia or dystopia in the future, it's, let's say, still an open question, but probably it will be not one extreme or the other, but somewhere in between, just like, say, technology has been transforming our societies, but at the end, we're still humans and machines will not replace us, but we're integrating more with us. And yeah, this vision of humanoid robots, I think non-humanoid robots are much more useful. And you can see them now, like in some cities, there are these delivery bots, but of course they have wheels. Autonomous vehicles and so on are much more useful than humanoid robots. In factories, non-humanoid robots are much more efficient because, let's say, in factory you want like a robotic arm that can do something very specific, and in many cases it's like huge, and you don't need all the extra things that you would get with humanoid robots. So these are more like toys or for social interaction. But then for conversation, they are still very weak, and that's, well, with LLMs, they're already improving considerably, but they don't understand, so you shouldn't trust. And that's precisely semiotics, which basically studies the relationship between symbols and meaning. And again, we can ignore meaning for telecommunications, but not for AI. And John Locke, in his essay concerning human understanding, divided science in three: the nature of things, that's one. Number two, that which man himself ought to do, which that would be more or less like ethics. And three, the ways and means which whereby one and two attained and communicated, semiotic, or the doctrine of science. semiotic in Greek. So yeah, like the bridge between the physical world and our actions, yeah, what we ought to do, that's what he calls semiotics. What's it, semiotike, or doctrine of science. And Ferdinand de Saussure coined the term semiology, study of symbols, and he has this concept of bilateral sign, meaning two-sided. So it's the signifier and the signified. So the signifier would be a word or a symbol, and the signified its meaning. So the question is whether these are arbitrary or not. Like in many cases, we can assign arbitrary meanings to symbols. And of course, in order to be useful for communication, those have to be shared. And I mean, we can also say that, okay, it's difficult to argue that machines understand meaning because it's also difficult to say what that is and how we do it. I mean, we assume that we understand meaning, but do we really understand meaning, and what is meaning at the end? So Charles Sanders Peirce advanced a lot in semiotic, and he proposed it as a formal doctrine of science. And compared to the Saussure, where there were two-sided signs, signs with two sides, let's say the signifier and the signified. In Peirce, there's a triadic, which includes the sign, the object, and the interpretant. So there's the sign, the object which it stands for, and then the agent making that interpretation. So this is also related to object, subject, and action of perception or cognition. And this has implications also for logic and mathematics. So I'll just read a quote. Nor must any syncretist say, I'm altogether myself and not at all you. If you embrace synergism, you must abjure the metaphysics of wickedness. In the first place, your nerves are in a measure yourself, and in far greater measure than without deep studies in psychology, you would believe. Really, the selfhood you like to attribute to yourself is for the most part the vulgarest delusion of vanity. Meaning that everybody around us defines us who we are. So let's say in a similar sense, one of the problems with meaning is that if we go to the dictionary to learn the meaning of a word, it's given in terms of other words. But then if we don't know what's the meaning of those words, then we go to the dictionary and it's given in terms of more words. So we end up with circular definitions that if we have a basis for the meaning on the real world and our experience on sensory motor contingencies, then that's useful. But if we just give a dictionary or encyclopedia to a robot, they won't understand anything. And actually, that's the theme of a short story by Boris Vian from 1950, which is futuristic about the 1980s. And there's this professor that precisely builds a robot that has the capacity to store the whole illustrated Larousse dictionary, which is like this. So, I mean, it was okay, yeah, like a CD-ROM in the 1980s. Another thing that happened in that story was that men had long hair and women had short hair, which, like, yes. But then in this futuristic world, the fact that the robot could read or store the information of the dictionary already made it capable of manipulating the signs in that book. And that's not the case. Still not the case. And then, I mean, I'll just finish spoiling the story for you. Uh, the the robot ends up with like a corny, cheap, romantic novel. I know in the United States they're very popular, but I forget the name of this genre. So let's say the robot starts behaving as one of the characters in that novel, which is funny. I mean, not realistic at all, because it's like, okay, where did he get all the context information to understand that book without the dictionary? But anyway, so many people try to study where does meaning come from, and here's Ludwig Wittgenstein. He was studied with Russell in Cambridge. Well, first of all, he was the heir of a very rich aristocrat Austrian family in Vienna. So his family controlled all the steel production in Austria. So it was a bit like the Carnegies of Austria. But I think there were four brothers, and two or three of his brothers committed suicide. And he enlisted in World War One in the Austro-Hungarian army, and he was fighting in the trenches. And in the trenches, he was writing his later called Tractatus Logicus Philosophicus, which was a big impact in philosophy. So, for example, the Vienna Circle, 1920s and 30s, were based strongly on Wittgenstein's Tractatus, even when by that time Wittgenstein was past that. So basically, like oversimplifying what he did in his Tractatus was like trying to put philosophy on on the basis of logic, and the conclusion was that we shouldn't speak about that which we cannot speak, and since we cannot speak about many things in philosophy, we should remain silent. So some people would say that he killed philosophy, but of course, many philosophers were trying to overcome the limitations that he noted. And afterwards, after the war, he became a rural school teacher, in part to escape suicide, because he had those tendencies, as his brothers actually committed suicide, or maybe one of them was killed in the war. I forget, but anyway. But then he also had problems there, and also he was homosexual, so that was problematic in the small rural Austria. So he went back to Cambridge, which in those years was a haven for gays. So that was, let's say, way better in that side. And he started interacting with Karl Popper, and then Alan Turing also took his classes. And with time, he developed new ideas. He was still interacting with Russell. Well, actually, Russell kind of brought him back to Cambridge. His teachers have very high respect for him, and he had a very difficult character. But anyway, some of his students kind of compiled notes that he had, because he didn't write formally like a book. So his famous philosophical investigations are actually collections of notes. But yeah, summarizing everything that he did in his philosophical investigations, which was how we understand, and he takes a pragmatic standpoint, basically saying that meaning comes from the use we make of symbols. So yeah, the meaning of a symbol is given by how we use that symbol. And this led later to some more refinement. So, for example, there's collective constructivism, where, let's say, this difference between the subject and the object. Of course, in science, we try to be as objective as possible, but then we need to describe those objects subjectively with symbols, with language. And then how we do this successfully is precisely because we construct that reality in a shared way. We agree at the same time on the symbols which we use and on the meaning that those symbols carry. So in a sense, with limits of my language means the limits of my world. And this is very close to discussions we've had already about the distinction between the map and the territory, between epistemology and ontology, object and subject, and so on. And there are many subfields that also study meanings, semiotics, how animals understand to take different actions, cognitive semiotics, also in artificial intelligence, about cultures, and also we mentioned second-order cybernetics. So, for example, in cultural semiotics, Roland Barthes speaks about simulacra, which basically he gives the example of Disneyland, which is not real because, let's say, it's like an artificial kingdom or world. But then we believe in it or acquire arbitrary meaning on how to behave in Disneyland. And I mean, it has been used also like, oh, this is just Disneyland, like something that's made up. But then, of course, we could argue that thanks to propaganda and marketing, most of our culture is also like that in the sense that it doesn't have a purely objective footing. There's always some arbitrary degree of how we interpret reality, and this has some advantages and disadvantages. Advantage that we can be creative, we have the freedom to give different meanings, and then yeah, there's freedom. Disadvantage that many people interpret or assign meanings in an arbitrary way for their own purposes, and that has led to many oppressive regimes, as we have been experiencing in many different countries, not only now, but throughout history. So fractals are spatial patterns. 1 over F noise would be their temporal similar, and this carries certain organization. This can be measured with information, and we can speak about the balance between signs and their meaning, and the open question whether machines will ever understand, but then we can ask ourselves whether we understand. For some reason, yeah. Any question?
So you mentioned there was like shared information and organization. The difference between shared information doesn't is more about the syntax of the meaning, but organization is more about the arrangement. Talk a little more about it. Make the difference between the two.
Yes. So Shannon, in his landmark paper, Mathematical Theory of Communication, somewhere he says like, okay, we assume that the meaning of symbols is already given. So it would be like in Morse code, you get the codes and then you know which letter. Or, I mean, you get any symbol and then you know what it means. So then that allows for the simplification of looking at the frequency of symbols, like what's the probability of the next symbol being 1 or 0 if it's a binary code. If it's an alphabet, what's the probability of getting one of the letters of the alphabet? And then he develops all the mathematics with those assumptions. In the first compilation, that he does with Wheeler, they kind of extended to like, oh, and if you want to include meaning, you just do like this. It's kind of too simplistic. And there have been many other proposals of trying to quantify semantic information. But again, we don't have a agreed definition of what's meaning and how, even less how to quantify it or how to relate it with thermodynamics. Because, for example, later Landauer was able to link this information to thermodynamics because Boltzmann gives entropy. So then there's this Landauer limit, which is the minimum amount of work you need to erase one bit. But then since meaning is arbitrary, information in general, let's say not only syntactic information, does not necessarily have to be conserved. So that has many implications. Because in physics, we are used to conservation laws of matter and energy, and then many things fit nicely. But for example, in economics, more and more we see that the value of things have no correlation with the amount of work required to produce them. And NFTs are, or Bitcoin, that's like one clear example that is just arbitrary meaning or arbitrary value. And that has impacts on the physical world. Yeah, I don't know whether I answered your question because I ended up like very different.
The opposite is the organization that's about the structure.
Yes. So when you measure information, Shannon's information, let's go to the different extremes. You basically have a probability distribution. So if you have zeros and ones, if you have the same probability, let's say you are tossing a fair coin, heads is 0, tails it's 1. So even if you have like 1 million data points, that will not allow you to predict the next coin toss. So the probability distribution has maximum entropy. I mean, according to equation, which is minus k, a constant, with the sum of the probability of having a symbol times log the probability of that symbol, and then the sum over all symbols. So if you have homogeneous distribution, then you have maximum entropy, Shannon entropy, because the next symbol will carry all the information that you need. If you have a highly skewed distribution, meaning that you know that the next symbol will be 0 or 1, so then you have a probability of 1 for one symbol and probability of 0 for all the other symbols. And that gives you an entropy of 0 because, let's say, by multiplying probability times the log of the probability, if the probability is 0, then everything is 0. And if it's 1, then the logarithm of 1 is 0. So then the next bit doesn't carry any information because you already know that it will be 1 or 0, whatever, because it has probability of 1. And then the opposite in organization, when you have maximum entropy, then you have the same probability of being in any state in a system. And then that's considered to be maximally disorganized or minimum organization. And the maximum organization is when you know exactly where everything is and you have maximum predictability, and that's minimum entropy. So if you normalize Shannon information to 0, 1, one can define organization as 1 minus Shannon entropy. Any other question? Yep.
I had a comment, short question. So you mentioned Charles Sanders Peirce, he was talking about how we have in a sense, what I understood is we are the product of the people around us, as in what meaning, I mean, what we see ourselves is not truly ourselves, it's those around us.
Mhm.
So if we take from a societal point of view, it sounds like he's kind of justifying segregation as in like a certain value in one system will be lost if we
Yeah.
stop. So am I reading too much into it, or maybe
I mean, it's interesting because next week we'll read this classic paper by Schelling, Dynamic Models of Segregation, which is that problem, but not necessarily related to semantics. But yeah, he speaks about, let's say, how people kind of form communities, and let's say similar people tend to flock together. And of course, we can say that that segregation is given by shared meaning. Because at the same time, if you have a diverse society, you will have competing meanings that try to propagate through the society. And in most cases, in a healthy society, you will have a big diversity, but then it becomes natural that people with similar meanings or similar ideas will gather together. No? And we observe that everywhere. In many cases, we have to force diverse people to interact, and it has benefits in many cases. Like Singapore does it precisely to avoid segregation of neighborhoods. And um, in the New England Complex Systems Institute, where I did my postdoc, Yanir Bayam and Mei Lim and others, just before I joined, they published a paper where they studied how a particular degree of segregation leads to ethnic violence. So basically, they kind of gathered data from violence in former Yugoslavia, India, and which other region? Was it Rwanda or I forget, there was a third region with ethnic violence. Um, and they found that the places where there was violence had segregation, but not too much, because let's say if you have maximum segregation, then it's like, okay, we are here, you are there, and we don't need to speak to each other, and it's fine. If you are well mixed, then you are kind of looking at each other all the time, and then let's say you also interact with each other without much problem. But then at intermediate levels of segregation, where you spend lots of time, but then you see those guys across the street and then they look at you in the wrong way and things like that, that's where violence occurs. Doesn't mean that always happens, but in those places that happened, they had these intermediate levels of segregation. Yeah. Okay.